Today we will take a look at section 5.1, exponential functions, period. To begin with, we'll take a look at the laws of exponents. These are from the review chapter in your book. Remember the product rule. When bases are the same and you're multiplying, you add the exponents. The quotient rule says when you have the same base and you're dividing them, you subtract the exponents. The power rule says when you're raising an exponent to another power, you multiply the exponents. The product rule, the product to a power rule, states when we have a product inside of the parentheses and an exponent outside, we can apply that exponent to each of the factors. This does not work when you have addition or subtraction in the parentheses. The quotient to a power rule says when you have a quotient inside the parentheses and an exponent outside, you can apply that exponent to the numerator and to the denominator. The zero exponent rule says anything raised to the zero power, except zero itself, is equal to 1. The reciprocal rule, or sometimes referred to as the negative exponent rule, says that when we have a base raised to a negative power, we can rewrite it as 1 over that same base raised to a positive exponent, a positive power. So for example, x to the negative third power would be equivalent to 1 over x to the positive 3 power. Then we have the definition of rational exponents. So a base raised to a rational exponent like 1 over n, where n is anything greater than or equal to 2, can be rewritten as a radical, the nth root of b. So notice that the denominator of your exponent becomes the index of your radical. The numerator of your exponent, the 1, becomes the power that you raise the base to. So this is b to the 1 power. So here's some examples. X to the 1/3 power becomes the cubed root of x to the first. X to the 1/5 power becomes the 5th root of x to the first. Well, when our rational exponent has a numerator other than just 1, let's say it's a different number, then b to the m over n power also can be rewritten in the form of a radical. And once again, the denominator of your exponent becomes the index. The numerator of your exponent becomes the power that you raise the base to. And we can write it like this, or we can write it with the exponent of m outside the parentheses. So x to the 2/3 power becomes the cubed root of x to the 2nd power. X to the 3/5 power becomes the 5th root of x to the 3rd power. What we're going to look at in this section is the exponential. We're going to take a look at the exponential function. We looked at about 9 different functions in the previous chapter, so we're going to add this to our list of basic functions. Remember when I went over that section with you, I shared with you that I wanted you to learn the name of the function, the basic equation, and the graph. So the same thing applies moving forward. The basic equation for the exponential function will be in the form f of x equals b to the x power. B is a number. It's a real number that is greater than 0, so that means it's never negative, and it cannot equal 1, because if we have 1 to a power, then that's just going to be equal to 1 no matter what that power is, unless of course it's 0. So we'd have f of x equal 1, which is just going to be a horizontal line. So here are the restrictions. B is any real number greater than 0 but not equal to 1. The x is going to be our exponent, and it's our variable. That is what is going to be changing. Now you may say, I thought we've had exponential problems before, but not exactly. We've had things like x to the 2nd power. Notice the variable was the base. Here the variable will be the exponent. Remember, x to the 2nd power gave us the shape of a parabola. X to the 3rd power gave us a curve that went through the 1st and 3rd quadrant. Now there's some characteristics of the exponential function that I want you to be aware of. We're going to take a look at the basic graph. What we have here on the left-hand side will be our exponential function whenever the base is a number greater than 1. It'll be an increasing exponential function. I like to say this is how you want your bank account to look. continuously increasing. On the right-hand side, this is what our exponential function will look like when the base is a number between 0 and 1. It'll be a decreasing exponential function. So notice the difference. Greater than 1, it'll be increasing. Less than 1, it'll be a decreasing. So for example, if this was 1/2 to the x power, notice the base is between 0 and 1, it's a decreasing. Notice this, the base is 2, it's greater than 1, it's an increasing exponential function. The domain and range of both of our exponential functions, notice from left to right, the x values will be -infinity to +infinity. The range for both of them, notice that our graph is approaching what we call a horizontal asymptote, a value of y equals 0 that it will never actually reach. And so this dashed green line is the horizontal asymptote. It's to your advantage to actually draw this in your graph on your paper to help you with the shape of the graph. So our lowest y value will be just above 0. So notice the parenthesis, and it will continue to +infinity in both graphs. So parentheses 0 to +infinity is the range. The horizontal asymptote will be represented by the equation y equals 0. Remember, that's how we write the equation of a horizontal line. Notice that our graph would pass the horizontal line test, so it is a 1-to-1 function, which means it will have an inverse, which we'll discuss later in the chapter. So one of the first things they want us to do is sketch the graph. So I'm going to show you how to do this on paper, and then we'll also take a look at how to use the tools in my math lab to sketch these graphs. It's to your advantage whenever you're graphing something other than a straight line to always use positive and negative values of x as well as 0. Alright, so here we're going to graph f of x equals 4 to the x power. Notice that our base is greater than 1, so it'll be an increasing exponential function, like the one here on the left. So I generate an x and y chart. Knowing the shape of my graph, I just generate a few points that I can then plot on paper. So I plugged in -1, 0, and 1. You'll notice on both graphs they always go through the point 0, 1 unless they've been shifted up, down, left, or right. Notice that if I plug in a 0 for x, you have 2 to the 0 power, which we talked about earlier. Anything to the 0 power is 1, except 0 itself. Alright, so if I plug in a -1 for x, that would be 4 to the -1 power, which is equivalent to 1/4. So I plot -1, 1/4. When I plug in 0 for x, that's 4 to the 0 power, which is 1. So I plot 0, 1. And then I put in x equal 1, that's 4 to the 1 power, which is 4. So I plot 1, 4. I then connect it with a nice curve, knowing the shape of my graph. I filled in the horizontal asymptote y equals 0 as a dashed line because I know the graph will approach this value but never cross over it. And there's our graph. Take a look at number 9. F of x equals 1/4 to the x power. Once again, I used the same values of x. This point here can almost be used as like let's say, like, you know how we use the vertex in the parabola to shift left, right, up, or down? Well, I like to focus in on this point as well to do the same thing when I have to shift a graph, which we'll get into in a moment. Alright, so when I plug in -1 for x, I'd have 1/4 to the -1 power. That would be equivalent to 4 to the +1. Remember the negative exponent rule? So we flip it. And so I plot -1, 4. Now starting off, notice my base was a number between 0 and 1. So I knew before I even started plotting any points, this would be a decreasing exponential function. When we put in 0, we have 1/4 to the 0 power, which is 1. And then when we plugged in a 1 for x, we get 1/4 to the 1 power, which is 1/4. So once I plot those and I fill in the horizontal asymptote, I know the shape of the graph, and we are done. Okay, taking a look at a few more examples, we have here now 2 to the -x power plus 1. Using some of the skills you learned in the previous chapter about transformations and reflections, remember now we have the basic exponential graph, and the +1 here added to the function is going to shift it vertically up 1 unit. The -x that's been inserted in the function is going to reflect it about the y-axis. Now, if you recall, there was an order of operations, an order of transformations that we talked about. And so we should go ahead and do that reflection first. So what we have here, if we started off with the basic exponential graph, going through the point 0, 1, it would look something like this. But what we're going to do is first reflect it about the y-axis, and if we do that, it would look something like this in green. Then we're going to vertically shift it up 1. Well, remember this point that goes through 0, 1 is being shifted up now to go through 0, 2. And the horizontal asymptote, which normally is at y equals 0, has been also shifted up 1 to now go through y equal 1. And notice we have it filled in as a dashed blue line. And so in blue, you have your final picture that we present for this function. Now, to actually plot points, notice I'm using the same generic points, -1, 0, and 1. Sometimes you have to choose more, but this is a good place to start. If I put in a -1 for x, that would be 2 to the negative times -1, which would end up being 2 to the positive 1 power plus this one here, and so you get 3. So notice -1, 3 is identified. Then when you plug in a 0 for x, that becomes 2 to the 0 power, which is 1. 1 plus 1 is 2. So we plot 0, 2. And then when I plug in a 1 for x, I get 2 to the -1 power, which is equivalent to 1/2, plus 1, which would give me 1.5. So I plot 1, 1.5. Having the horizontal asymptote really helps because I know this portion of the graph will approach it but never cross it. And then this will extend up to infinity. So identifying the domain, left to right, we have from -infinity to positive infinity. The range, the bottom of this graph, will start at 1, but not include it, and go to positive infinity. The y-intercept, the place it crosses the y-axis, is right here at the value of 2. And the horizontal asymptote is the line, the horizontal line, y equals 1. All right, take a look at this graph. And using the information from last chapter, we know the -3 is going to shift the graph down 3 units. The fact that the base is between 0 and 1, we know this is going to be a decreasing exponential function. So we know a lot about it before we even get started based on the things we've learned. So plotting these points, plugging them in for x, these are the coordinates I got, and I filled in my horizontal asymptote because I knew it was going to shift from y equals 0 down to y equal -3. You then are able to identify the domain and range and the y-intercept, the place where it's crossing the y-axis. Okay, we're going to take a look at how we would graph a problem using the keys that are presented to you in the homework in the My Math Lab. And so I'm going to find one of those examples to show you here. So let's see, I think it was starting with the 9th problem. Yes. All right, so when you take a look at this, we want to plot 2 to the x minus 2. Since the base is greater than 1, we know this is going to be an increasing exponential function. The -2 we know from the previous chapter is going to shift the entire graph to the right 2 units. So when you click on your graphing tool, notice they have an exponential graph for you. You're going to click that and then just click anywhere on the graph. It's going to fill in the basic exponential. Notice going through this point 0, 1. You're then going to use these tools here to shift it accordingly. Notice we have a vertical stretch, a vertical shift, a horizontal stretch, a horizontal shift, reflection about the x, reflection about the y. And we also have a place to adjust the base if necessary. Okay, and so what we're going to do right now, it's already set on a base of 2 for us. So we said we're going to shift to the right, horizontal shift. So notice I'm moving the horizontal shift button 2 places to the right. Notice it was highlighted at 2. Once you're done doing that, hit save and then hit check, and your answer will let you know whether or not you got the problem correct. All right. Okay, taking a look at this example, notice that we are going to do a few different transformations on our graph. We are going to shift it to the right 2. We are going to reflect it about the x-axis, and then we are going to shift it up vertically 2. And that is according to the transformations, the order in which we should go. So horizontally, we're going to be shifting it to the right 2, so that's this one here, and then we're going to reflect about the x-axis, and then we are going to vertically shift it up 2. So the order does make a difference. I'm going to hit save and check, and we're good.